So this question is from, I think, the 2019 paper 2A, and it's involving point estimates and estimates of the population mean. So Anna has taken made point estimates of the mean height of trees in 3 different areas of the forest. So she's done them all on the same day. The mean height of this group of 10 trees is 16.8. The mean height of this group of 15 trees is 18.4. And the mean height of this group of 5 trees is 15.9. And you're asked to work out the best estimate of the population mean. So the way we're going to do this is multiply. So if we've got 10 trees with a mean height of 16.8, then if we did the total of all those trees, we would do 10 times 16.8, or 168. And 15 trees with a mean height of 18.4. So we'll do 15 times 18.4 to give us the total height of those trees. And that gives us 276. You can put this in your calculator. And similarly for the last one, 5 times 15.9. And that gives us 79.9. And when you add the totals up to get the total height of these 35 trees, you get 523.5. And so because we want to get the best estimate of the population mean, we are going to divide this by the number of trees that we were investigating here. So we had 30 trees. So if we divide this number, 523.5, and divide it by 30, we get 17.45, which is the best estimate of the population mean. So in this part B, we are using a random 3-digit number provider, but we're using it. So Anna wants to get a sample of 10 trees, but the trees numbered from 1 to 225. The trees are, just numbered from 1 to 225, and she wants 10 of those. But she hasn't got a random number generator, that's the word, but just between 1 and 225. So she's using 3-digit random numbers. So we've got to figure out what they've done here to get from this random number generator with 3 digits to get a tree number in between 1 and 225. So you might have spotted that if the number is less than 225, like here, it's going to be the same. 167 is the same. I think they're the only ones. So what we're going to do is, because we've only got trees 1 to 225, if the number generated was 226, we're going to go back to tree 1 again. If the number generated was 227, we're going to go back to tree 2, etc., until we've done a whole nother chunk of 225, which takes us up to 450. So then for the 451st one, we go back to 1. So we're just going to use these numbers to count from 1 to 25, 225, and once we've finished, back to the beginning again. So for example, 850, in fact, let's work out how many lots of 225 we've got, or what our multiples of 225 are. So 2 lots of 225 will be 450. Another lot of 225 will be 675. And then another lot after that would be 900. So for 850, what we've done is we've said, well, I'll discard the first 225. And actually, by the time I get to 900, that's too many. So I'm gonna stop at 3 lots, and I'm gonna say 675 would be 225. So 676 is going to be 1 again. 677 is going to be 2. So actually the easiest way to do this is just to say 850, take away 675, and that will tell us what our tree number would be. We're just taking away chunks of 225, and that would give us 175. So this is just to prove the method that's being done. So for 580, if we were to take away 2 chunks of 225, we should end up with 130. So let's look at what we've been asked to do. We've been asked to create the random tree numbers from these 3 randomly generated 3-digit numbers here. So 50 is fine because that's less than 225. We can keep that one the same, just like we did with these previous ones. 425, we're going to take off a chunk of 225. In fact, we can just take off 225 because once we do that, that leaves us with 200, and we've got a tree that's numbered 200. So that one will be 200. 662, I think if we took off 1 lot of 225, that still wouldn't be enough. So we'll take off 2 lots of 225, which is 450. So 662, take away 450, will give us 212. So the tree number here is going to be 212. So basically, you are the random number generator. Every time it hits 225, you restart your tree numbers again. So in this part of the question, we are given 3 different parts of data for each tree, the diameter, the height, and the age. And Anna wants to use the diameter to estimate its height and to estimate its age. And we've got to work out which of these is most likely to be reliable. And actually it's told you here to use the PMCC to help you decide. So what you need to do is work out the product moment correlation coefficient for the diameter and the height together. So inputting both of those bits of data into your calculator, and then note down the PMCC for that, and then you're going to use the diameter and the age and work out the PMCC for that. And then whichever one is the highest number, the strongest correlation, that will be the one that we'd use, or which is the most accurate to estimate. So for example, if you're using diameter and height, you will get your calculator, and if you've got a Casio and a ClassWiz a bit like mine, you'll probably go to menu, choose statistics, which on mine is number 2, and then you look for the one that says y equals a plus bx, which is number 2 on mine. Then you get to that bit where you can input all your data. So you'll put all your diameters in the X column, and you press equals each time you've entered one. Then you put all your heights to start with in the Y column. Make sure you've got the same number in both columns. And then if your calculator is like mine, you'll go to the option button and look for regression calc, which on mine is number 4. And then that will give you values of A and B and R, which is the PMCC. So you do that for diameter and height. Then you clear your calculator, or make a note of it, clear your calculator and do diameter and age and see which number's higher. And it turns out that the diameter and the height is 0.89-ish. The diameter and its age is 0.81. So if you remember, a perfect positive correlation is when R equals 1. So this one here is closer to that. So the estimate that's going to be more reliable is using the diameter and its height.